Hello everyone. Let's talk about something truly amazing in the world of wireless technology. Imagine you have a special kind of screen, a filter, but not for coffee or water. This screen is for invisible waves, like the ones your phone uses to connect to the internet. We call these screens frequency-selective surfaces, or FSS for short. They are thin, repeating patterns of metal printed on a surface. Their job is to control which radio waves get through and which ones are blocked. This is incredibly important for making sure our wireless devices work without interfering with each other. It's science in action, helping our gadgets communicate clearly and efficiently every single day. Now let's consider how these surfaces work. Think of them as bouncers at a club, but for frequencies. Some frequencies are on the VIP list and get to pass right through, while others are turned away at the door. We can design an FSS to do one of two main things. The first is called bandpass. This type lets a specific range or band of frequencies pass through it. The other type is called bandstop, and it does the exact opposite. It blocks a specific band of frequencies while letting all the others go on their merry way. This simple idea of allowing or blocking signals is the foundation of so much modern wireless communication. Let's look closer at these two types. The bandpass FSS is often made of a mesh-like pattern, kind of like a window screen or a net. These are called mesh-type or aperture-type FSS. The openings in the mesh are designed to resonate at certain frequencies, allowing those waves to travel through unimpeded. On the other hand, the bandstop FSS is usually made of a grid of separate metal patches. These are called patch-type or element-type FSS. Each little patch acts like a tiny mirror, reflecting a specific range of frequencies away. So, one lets the right signals in, and the other keeps the wrong signals out. It's a very clever way to direct traffic on the invisible highways of our airwaves. So why is this so useful? Well, consider all the different signals flying around us right now. Wi-Fi, Bluetooth, 5G, GPS, they all use different frequencies. An FSS can be used in the wall of a building to let cell phone signals in, but block out other signals that might cause interference. It can be used in a satellite dish to focus on the desired communication channel. Or, it can be integrated into an antenna to improve its performance by filtering out unwanted noise. By carefully designing these surfaces, engineers can create a more organized and reliable wireless world for all of us. It's all about controlling the electromagnetic spectrum, and FSS are one of our best tools to do it. When engineers design an FSS, they have a whole toolbox of structures and shapes to choose from. The simplest and most common type is the infinite periodic structure. Now, of course, nothing is truly infinite, but we model it this way when the surface is very large compared to the wavelength of the signal it's controlling. Think of a huge wall covered in a repeating wallpaper pattern. That's the basic idea. Another type is the cascaded FSS, where multiple layers of these patterned surfaces are stacked together with some space in between. This layering technique allows for much sharper filtering, creating a more precise response that can block or pass frequencies very effectively. Next, we have finite periodic structures. These are FSS that are not infinitely large, which is, of course, the case for any real-world device. When the FSS is small, the edges start to matter a lot. The waves can diffract or bend around the edges, which changes how the FSS performs compared to its infinite cousin. Engineers have to use sophisticated computer models to account for these edge effects to make sure the FSS works as intended in a compact device. Then there are curved FSS. Instead of being flat, these surfaces are shaped to fit on a curved object, like the nose cone of an airplane or a sleek modern antenna dome. The shapes of the little metal elements themselves are also incredibly important. The design journey often starts with very simple shapes like squares, circles, or crosses. These are known as classical elements. A grid of simple metal squares, for instance, creates a basic patch-type FSS that stops a certain frequency. A grid of cross-shaped slots cut into a metal sheet creates a basic mesh-type FSS that lets a frequency through. The size, spacing, and shape of these elements all determine exactly which frequencies are affected. Changing the length of a cross's arms, for example, will tune the FSS to a different frequency. It's like tuning a guitar string to get a different note. To get even better performance, designers have moved beyond these simple shapes. They use more complex geometries to make the FSS work over multiple frequency bands or to make it smaller. For instance, instead of a simple cross, they might use a shape that looks like a snowflake, a fractal. These intricate designs can interact with waves in very complex ways, allowing for more sophisticated filtering. Other techniques involve using multiple layers, each with a different pattern, or using special materials for the board the FSS is printed on. All of these design choices work together to fine-tune the FSS for a specific job, whether it's for your home Wi-Fi or a deep space satellite. As our electronic devices get smaller and smaller, the components inside them have to shrink too. This is a big challenge for FSS design. A traditional FSS element, like a simple patch or cross, needs to be a certain size to interact with a specific radio wave, usually about half the length of the wave itself. For lower frequencies, like those used in some mobile communications, the waves are quite long. This means the FSS elements would have to be very large, too large to fit into a smartphone or a small sensor. This is where the science of miniaturization comes in. The goal is to create a miniaturized-element FSS that can do the same job but in a much smaller space. One of the first steps toward making FSS smaller was to move away from simple patch and wire arrays. Engineers realized they could make the electrical path on the FSS element longer without making the element itself bigger. Think about it. How do you fit a long piece of string into a small box? You coil it up. The same idea was applied to FSS design. Instead of a straight wire, they started using meandering or looping paths. This led to the development of loop wire and loop-loop structures. These designs pack a longer electrical current path into a smaller physical area, allowing the FSS to resonate at lower frequencies while remaining compact. However, this miniaturization came with its own set of problems. One of the biggest challenges is something called insertion loss. When you make the elements smaller and more complex, they can become less efficient. They might absorb or reflect some of the energy of the signal you actually want to get through, which is not good. It's like trying to listen to someone whispering from across a noisy room. The message gets weaker. To solve this, scientists developed clever designs, like combining loop elements with straight wire grids. This loop wire FSS design offers a good compromise, providing miniaturization without sacrificing too much performance. The evolution didn't stop there. Further improvements led to designs that are even more compact and efficient. We now have FSS based on convoluted space-filling curves and other advanced shapes that are incredibly good at packing a lot of electrical length into a tiny footprint. These are often inspired by metamaterials, which are engineered materials with properties not found in nature. By carefully arranging these tiny, intricate structures, we can create FSS that are stable, have low loss, and can be easily integrated into the smallest of our modern gadgets. This journey of making things smaller is what allows technology to keep advancing. The world of wireless communication is constantly changing. New standards like 6G are on the horizon, and we have more devices connecting to the network than ever before. In this dynamic environment, an FSS that only works at one fixed frequency is like a radio that can only tune to one station. It's not very useful. This is why the future of FSS lies in making them tunable or frequency agile. A tunable FSS can change its filtering properties on the fly. It can adjust the frequency it passes or blocks in real time, adapting to different needs or changing signal conditions. This makes our wireless systems much more flexible and intelligent. So, how do you make a static pattern of metal tunable? The secret is to add active components into the design. One of the most common ways to do this is by incorporating something called a varactor diode. A varactor is a tiny electronic component whose capacitance, its ability to store an electrical charge, changes when you apply a voltage to it. By placing these varactors at key points within the FSS elements, We can electronically control the surface's resonant frequency. Applying a different voltage changes the varactors, which in turn changes how the FSS interacts with radio waves. This is like having a remote control for your frequency filter. The benefits of combining miniaturization with tunability are enormous. Imagine a smartphone that needs to connect to many different wireless services, 4G, 5G, Wi-Fi at different frequencies, Bluetooth and GPS. Instead of having a separate antenna and filter for each one, a single, compact, tunable FSS could handle many of these jobs. This not only saves a huge amount of space inside the device, making it smaller and lighter, but it also improves performance by reducing interference between all these different systems. It paves the way for truly smart devices that can seamlessly switch between different communication standards. Ultimately, the development of miniaturized and tunable FSS is a critical step toward the next generation of wireless technology. These advanced surfaces are not just filters, they are smart, adaptable gatekeepers of the electromagnetic spectrum. They will enable everything from more powerful and compact personal devices to advanced radar systems and secure satellite communications. By continuing to innovate in FSS design, we are unlocking a future where our connections are faster, more reliable, and more versatile than ever before. It's a fantastic example of how fundamental science and clever engineering come together to change our world.